All right. In this example, we have a CO2 cartridge used to propel a small rocket cart. By the way, these kinds of rocket carts actually are used in competitions. People have little CO2 cartridge rockets and they race them. So this is kind of an interesting problem. So we're told that the compressed carbon dioxide is stored at a pressure of 41.2 megapascals absolute. So that's a stagnation pressure. It's the pressure inside this kind of the cartridge, so it's essentially at stagnation conditions. Temperature is 20 degrees C, and it's expanded through a smoothly contoured converging nozzle, sort of shown here with the throat area of 0.13 square centimeters. And we're told to assume that the cartridge is well insulated, so there's no heat loss out of the cartridge, and that the pressure surrounding the cartridge is 101 kilopascals. So this is what the back pressure is. We're discharging into this pressure. So for the given conditions, what we want to do is calculate the pressure at the nozzle throat, determine the mass flow rate of carbon dioxide through the nozzle, so what's the rate of mass leaving this cartridge, determine the force required to hold the cart stationary. So if we're going to apply force to this, what force do we need to apply to hold this thing in place? Sketch the process on a TS diagram. Part E is what range of cartridge pressures will the flow through the nozzle be choked. Part F, will the mass flow rate from the cartridge remain constant for the range of cartridge pressures you found in Part E? So that's an interesting one. We have to explain that answer. And finally, Part G, write down but do not solve the differential equations describing how the pressure within the tank varies with time while the flow is choked. So there's a lot going on in this problem. So let's get to it. Oh, the last thing I should mention is we're given some conditions for carbon dioxide as an ideal gas. So we have the ideal gas constant for CO2 and the specific heat ratio for CO2. All right, so let's get started. First thing we're going to do is calculate the pressure at the nozzle throat. So the idea here is let's determine whether or not the flow through this converging nozzle is choked or not. If the pressure at the if the Mach number here is equal to 1, then we know the pressure here will be the sonic pressure, P star. If the Mach number is less than 1, then it'll be a subsonic flow there, and then the exit pressure will be equal to the surrounding back pressure. It's not going to be a supersonic flow because we're going from stagnation conditions through a converging nozzle. So at best, the flow is going to be subsonic going through this converging section. And at the exit, at the throat, it'll either be subsonic conditions or sonic conditions. It can't be supersonic conditions. So we're going to just check to see whether or not the flow is at sonic conditions at the throat. And the way we do that is we're just going to see how this back pressure to stagnation pressure ratio compares to the sonic pressure to stagnation pressure ratio. So what I'm saying is we're going to just check to see if the back pressure to the stagnation pressure, we're going to see if that is less than or equal to the sonic pressure to the stagnation pressure. And if that's true, so if that's true, then we'll have a choked flow. Actually, I can remove the question mark here. It'll be a choked flow if that's true, because the back pressure would be low enough that it's causing the flow to accelerate to sonic conditions at the throat. So that's what we're going to check. So our back pressure here is going to be the 101 kilopascals. We're doing everything in terms of absolute pressure. P naught is the 41.2 megapascals. The P star over P naught, since we're dealing with CO2, we have to actually do the calculation to find out what that ratio is. Remember that that's equal to 1 plus the specific heat ratio K minus 1 over 2 raised to the K over 1 minus K power. And here our K is equal to 1.30. So it's not the same as air, so we actually have to calculate that value. And when you work out the numbers, that comes out to be 0.5457. So when we take this ratio on the left-hand side, that'll come out to be 2.45 times 10 to the minus 3. So clearly that is much smaller than P star over P naught. So indeed the flow is choked at these conditions. Okay, so we know that the flow is choked, and since the flow is choked, that means that the Mach number at the exit will be equal to 1, which means that the pressure at the exit will be the sonic pressure. And we can find that sonic pressure by just using this ratio that we just calculated a moment ago. Since P star over P naught is 0.5457, we can find P star because we know P naught is the 41.2 megapascals. So PE is equal to P star, which is equal to P star over P naught times P naught. We know that this is the 41.2 megapascals, and this ratio we said just moments ago was 0.5457. So PE comes out to be 22.5 megapascals. And just as a reminder, that's an absolute pressure. All right, so far so good. Let's go back up. That's part A. Now part B is to find the mass flow rate of CO2 through the nozzle. Well, since the flow is choked, the mass flow rate will be the choked flow mass flow rate. And we can find that by using one of the formulas we derived in our lecture. It's also on the formula sheet. So you can look that up there, and I'll just write it out. I think I've written it down correctly here. But it comes from the formula sheet. So this is our choked flow mass flow rate. And we know all of the quantities here. We know K is 1.3. We have to make sure we're doing this for carbon dioxide. P naught was the 41.2 megapascals. It's an absolute pressure. R, we were given in the problem statement right up here that it's 189 joules per kilogram Kelvin. The T naught we're given, it's 20 degrees, but remember we have to convert that over to an absolute temperature. So T naught will be 20 degrees plus 273. So it'll be 293 Kelvin. And then the last little bit is the A star, but the A star will be the throat area. But remember that the Mach number here is equal to 1, so that means that the sonic conditions here, so that means that the throat area is actually the sonic area. So the area at the exit is the sonic area, which is 0.13 square centimeters. So we can take those numbers, plug them in, and work it all out. And what you'll get is m dot comes out to be 1.52 kilograms per second. So that's how we find the mass flow rate. Now let me just mention for a moment here what would happen if we found that the flow was not choked. If we found that this ratio was greater, a greater than symbol, then it would mean that the flow is not choked, which would mean that the Mach number at the exit would be less than 1, and that means that the exit pressure would be equal to the back pressure in that case. When you have a subsonic flow exiting, if it's a subsonic flow exiting, then the exit pressure will be the same as the back pressure. So we would have in that case the exit pressure and back pressure being the same. And then to find the mass flow rate, we could use the isentropic relations to find the temperature here. So that would be the T over T naught is equal to a function of Mach number expression. So we could get the temperature here, we'd have the pressure here. We could then find the density from that. We would know the area there. We would have the density from the ideal gas law. And we could find the velocity there because we could find the Mach number at that point because we'd know the pressure there and use the stagnation pressure ratio to get the Mach number from that. From the Mach number and temperature, we could ultimately get the velocity there, and you could just do m dot equals rho v a. I know I just said a lot there. If you didn't catch it all, just replay the video and you can hear what I had to say. But that would be what we would do if the flow was not choked. Okay, well anyway, it's choked here, so let's continue to move on. So the next part is determine the force required to hold the cart stationary. Now for this, we're going to apply the linear momentum equation. So we have to go back to the material that we covered earlier on in the course. What we do is draw a control volume. that surrounds the cart and the CO2 cartridge. So there's our control volume. Let's put a coordinate system on here. So we'll call that the x direction, the y direction. Nothing is moving here, so it's an inertial frame of reference. And then we would apply the linear momentum equation. So let's write that out. So the linear momentum equation in the x direction. Let me write it all out, and then I'll go ahead and explain what each term comes out to be. So you have to remember back to some material we covered in the course, a month or two ago. Okay, so there's our linear momentum equation in the x direction. Let's start with some easy things. Body force in the x direction, that's 0. The gravity, just from the picture, it looks like it's pointing downward. This term is an interesting one. If you look up at the problem, it's actually not a steady problem because there's mass leaving our CO2 cartridge, right? So it starts with a certain amount of mass and then it discharges. So the mass is decreasing in time, so it's not a steady problem. However, most of the mass inside this control volume, the cart and all this CO2 inside here, has essentially 0 velocity, right? Because it's at stagnation conditions. So this term is actually about equal to 0, not exactly equal to 0, but about equal to 0 because the ux is about equal to 0 for most of the mass inside there. So it's not 0 because it's steady, it's 0 because the x velocity is very small for most of that mass. The surface forces in the x direction, that'll just be the applied force F. If we come back up here, we see our surface force F applied there. Everywhere else around here is at the surrounding back pressure of 101 kilopascals, right? It's 101 kilopascals everywhere here, including the exit, because we found, oops, I'm sorry, I made a mistake there. We do have a pressure force now that I look at it. We said that at the exit we have sonic conditions. So it's all atmospheric pressure everywhere except right at the exit. At the exit, the pressure is that pressure right there. It's the sonic pressure. So our surface forces will be the applied force plus we have our exit pressure minus the surrounding atmospheric pressure times the area of the exit. Okay, so let me just redraw the picture here so I don't have to go back up. So here's our CO2 cartridge. This is our control volume. It's not a very good picture, but the pressure right there, let me draw this in, that pressure there will be P exit, which we know is P star. And if you think about just the projected area going across this way, then the corresponding pressure force on this side would be the P atmosphere acting on the same area. So I've got the sign wrong based on that picture. This should actually be a minus here because it's the pressure at the exit here. Remember, the pressure force always acts inward on the area. That's why it's acting to the left here. So it'll be a minus PE times AE. And then here, this one points to in the positive x direction, so that makes it a positive P atmosphere times AE. So that's our surface force. Okay. The last thing that we have is our momentum flux term. And this one will be the velocity at the exit. So that's this term. That's in the positive x direction. This is just the velocity at the exit. And then multiplied by the mass flow rate. That's this whole term. And it's a positive because the flow is going out of the control volume. So when you do this dot product, it comes out to be a positive 1. All right, so hopefully all that makes sense. This one's the trickiest part of this by far is this term right here. Just keeping in mind that because we have sonic conditions here, the pressure at the exit is not the same as the back pressure or the atmospheric pressure. It's actually different. And so that contributes to the surface force on that control volume. So that's why we have to include that. So let's go ahead and rearrange that equation to solve for the force F. So the force F will be m dot times VE plus PE minus P atmosphere, or that's really the back pressure times AE. Okay, now at this point we need to, if you look at this, you'll see that we already know the mass flow rate. We calculated that previously. We know the pressure at the exit. That was what we calculated right up here. So we have that one. We have the mass flow rate. We know the atmospheric pressure. That's just the back pressure. That's given right here, the 101 kilopascals. We know the area of the exit. We said that's the sonic area. That was right up here. The only thing we don't know is the velocity at the exit. So we have to find that. So the velocity at the exit will be equal to the Mach number at the exit times the speed of sound at the exit, right? And then the speed of sound at the exit is the square root of kRTE. We're treating the carbon dioxide as an ideal gas. Now the Mach number at the exit is just equal to 1, right? It's at sonic conditions, so that's easy. We still need to find the temperature at the exit. Oops, sorry about that. So the temperature of the exit we can find from our stagnation temperature expression. So T at the exit over T naught is equal to 1 plus K minus 1 over 2 times the Mach number at the exit squared, all raised to the minus 1. But we know the Mach number at the exit is equal to 1. We know the stagnation temperature was the 293 Kelvin. It was 20 degrees C, and we add in the 273 to make an absolute temperature. And then we know, of course, K is the 1.3 because it's carbon dioxide. So from this, we can solve for the temperature at the exit. And that temperature at the exit comes out to be 255 Kelvin when you work out the numbers. So we can plug that in up into here and then solve for the velocity at the exit. And so when you plug those numbers in, the velocity at the exit comes out to be 250 meters per second. So that's the velocity at the exit. And now that we have that, we can plug that back in up into here, and then we can solve for the force. So when you do all that, the force comes out to be 671 newtons if I plugged all the numbers in correctly. Okay, so that one's a little tricky because there's a lot to it. You have to use the linear momentum equation, and probably the hardest part by far is just recognizing that there's this additional surface force because the pressure at the exit is the sonic pressure and it's not equal to the back pressure. Okay, so let's continue. So that's part C. Part D is sketch the process on a TS diagram. So let's do that. So here's our TS diagram. We're starting from stagnation conditions up here. So here's the stagnation temperature. Here's the stagnation pressure. So we're going to start from there. And then we go isentropically to the throat, or the exit. In this case, the throat and exit are the same thing. And that's at sonic conditions. So this will be T star. We go isentropically, so we go straight down. And then this will be P star. Right? The exit is at sonic conditions. So it's the sonic temperature and the sonic temperature and sonic pressure. Now, the back pressure is will actually be considerably lower, right? Like, let me go back up here and show you. So what we've done is we've done the TS diagram from here to right at the throat. Let me go ahead and just continue it to the surrounding back pressure. You'll notice that the surrounding back pressure is quite a bit lower than the exit pressure, right? So what ends up happening in that case is the following. And what you'd find actually is that the surrounding temperature is actually higher than the exit temperature. So what that would look like is we would have a back pressure that's quite a bit lower. So here's our back pressure. So you can see that this curve falls below this one. If I continued them, you'd see it falls below. And then the temperature of the surroundings would be somewhere like this. This would be the back temperature. And what ends up happening is as the flow comes out, it'll go from our sonic conditions up to here in a non-isentropic manner. This is a part we haven't discussed how you would analyze that exactly. All I can say is that that process occurs non-isentropically. It's kind of a complex process. I talk about it in the lecture that you go through these expansion fans and you get a lot of mixing that would occur. The mixing results in non-isentropic conditions. You know from thermodynamics that when you have mixing of fluids, that's a non-isentropic process. But anyway, so it occurs non-isentropically. That's why the entropy is increasing back to this, to the surrounding back pressure. This is the atmospheric conditions. So that's what that would look like. And normally in this course, all we would care about is this part. But just for the sake of being complete, I thought I'd show this part in there. Okay, so that's the TS diagram. Let's see what else we have left to do in this problem. There's a lot to it. Part E, what is the range of cartridge pressures for which the flow in the nozzle will be choked? So that's getting back to this expression here. We want the flow to be choked, so we want this to hold true, and what we're trying to figure out is what value of P naught will make this true. So what we can do is just rearrange this expression. This side will stay the same. P star over P naught will still be 0.5457. So let me write that down here. So we have PB over P naught. We want that to be less than 0.5457. That's equal to P star over P naught. Right, so I can just rearrange that expression. I want P naught to be greater than or equal to PB all over 0.5457, where PB is the 101 kilopascals. It's still going into the same back pressure, right? So we can solve that, and what you'd find is that the cartridge has to be above, the cartridge pressure has to be above 185 kilopascals absolute in order for it to remain choked. So it'll remain choked as long as P naught is greater than 185 kilopascals. So it's really just going back to that expression that we started with in this problem. So if as long as the cartridge pressure is at that is at a pressure higher than 185 kilopascals, the flow will be choked. As soon as it drops below 185 kilopascals, then what will happen is the flow will no longer be choked. The Mach number at the exit will be less than 1, and then the exit pressure will be the same as the back pressure. Okay, so let's go back up to the next part. Will the mass flow rate from the cartridge remain constant for the range of pressures you found in part E? So when the flow is choked, will the mass flow rate be the same? And the answer to that is no. And the reason why is, if you go back to this expression for our choked flow mass flow rate, certainly this part is a constant. The sonic area is still going to be the sonic area. The flow's choked, so the exit area is A star. Stagnation temperature is constant in this particular case because we're told we're told somewhere in here that the cartridge is well insulated. And what you'd find under those conditions is basically the stagnation temperature remains constant. Actually, I take that back. The stagnation temperature would change. It would actually start going down. I apologize for that. But sorry, I went too far. So what would happen is the stagnation temperature would go down, and in particular, the more important thing is that stagnation pressure is decreasing. As you discharge mass from inside this cartridge, the pressure in here is going to go down. Okay, and so since that pressure goes down, this term is getting smaller, and then your mass flow rate will go down. Okay. As far as finding what the stagnation temperature is as a function of time, you'd have to go to the first law and do an analysis on that. And I'll talk about that in just a moment. But both the stagnation pressure and the stagnation temperature drop as you discharge material, but it's really in such a way that the mass flow rate will actually decrease as time goes on. So let's do the last bit of this problem. Write down, but don't solve, the differential equations describing how the pressure within the tank varies with time while the flow is choked. So let's write those down. This is where things get pretty complex. So in order to find how the conditions inside the cartridge change with time, what we're going to do is apply conservation of mass to the same control volume that we used for the linear momentum equation. And I'm going to just do this a little faster so this video doesn't take a huge amount of time. But what will happen for conservation of mass, it'll say the time rate of change of mass inside the cartridge, so this is the mass in the cartridge, that will be equal to minus m dot, so the rate at which mass leaves the cartridge. And we know that that's just the choked flow mass flow rate, right? So this is this expression that we'd already written down. I'll write it down again. Okay, so that's our expression for how the mass inside the cartridge changes with time. And the thing is we just have to keep in mind that the stagnation pressure is going to change with time. So what I'm going to do is I'm going to use the ideal gas law, as well as let me go ahead and use the ideal gas law to rewrite this expression. So let's see, we're going to do P naught is equal to rho naught R T naught. So that just comes from the ideal gas law, and I'll substitute that in here. So this will end up being all of this stuff. I'm not going to repeat it, but it's all of this just repeated down here. And then this will be rho naught R T naught times the square root of K over R T naught. What I'm trying to do is get everything in terms of the same variables. And then the density inside the cartridge will be the mass inside the cartridge, m naught, divided by the volume of the cartridge. Okay, so this will be the following: m naught all over v. V is the volume of the cartridge. And then we'll have the square root of kr T naught when I multiply these two things together, times A star. So that's how our mass inside the cartridge changes with time. And I could, of course, rearrange this a bit. You know what, actually, I'm not even going to do that. I'll just leave it as is. Let me go ahead and leave that. So here we have one differential equation. When you look at that differential equation, the thing to keep in mind is, we'd certainly have the mass in the cartridge. That's going to be changing with time. But the temperature inside the cartridge could change with time as well. So the things I'm highlighting change with time. Everything else will remain constant while the flow is choked. Now the other thing that we'd have to do is apply the first law to the same control volume. This is not something we've really covered in our course, but it is something that was covered in thermodynamics. And again, let me just write this out, and then I'll explain what it is. So I'm just going to write the whole thing out. I'm just going to write the whole thing, and then I'll describe it all. Okay, so this is our first law analysis. What this term is this is the time rate of change of total energy inside the control volume. So this is the mass inside the cartridge, and this is the internal energy inside the cartridge. So that's the specific heat at constant volume times the temperature inside the cartridge. Remember that specific internal energy looks like this, right? For an ideal gas, it's du is equal to Cv dt for an ideal gas. So that's what I've done here, is I've done this for an ideal gas. And then we have, this is the this term is the rate at which total enthalpy is leaving the control volume through the control surface. So there's the mass flow rate out of the control surface. This is the specific enthalpy out of the control volume. So that's the specific heat at constant pressure times the temperature at which it's leaving the control volume. There's the kinetic energy term. I'm not going to factor in the potential energy term because we're dealing with a gas. So this is the time rate of change of total energy within the control volume. This is the rate at which total enthalpy leaves the control volume. That's equal to 0. Normally on this side, in the first law, you would have the rate at which heat is being added to the control volume plus the rate at which other work is being done on the control volume. But in this case, The control volume is well insulated, and there is no other work besides pressure work which is factored into the specific enthalpy. Again, this expression, you have to go back and think about your thermodynamics first law analysis. Okay, so it's not something we've covered in ME 309, but it would be something that was covered in ME 200. Now, in this expression, we'll assume that we're dealing with a perfect gas so that CV and CP are constants. We already talked a little bit ago about how the temperature at the exit can be found from our stagnation temperature ratio. Looks like that. Remember, the Mach number at the exit is equal to 1. So we can get our expression, so we can solve for our temperature at the exit in terms of the stagnation temperature. Similarly, we talked before about how we can find the velocity at the exit. It's just the Mach number at the exit times the speed of sound at the exit. And of course, the Mach number at the exit while the flow is choked is 1. So we can find the velocity at the exit from this expression, where TE we just found up here. And so then you see that we have a second differential equation that involves the mass inside the control volume, the stagnation temperature inside the control volume. The m dot just goes right back to this expression, which we've already talked about. This is the choked flow mass flow rate. Again, we'd follow the same. It's basically what's written over on this side. So this whole bit here, let me use a different color. This whole bit here goes right in there. So what we would have at this point is two coupled differential equations, both involving the mass inside the cartridge and the temperature inside the cartridge. Right? Ultimately, these terms TE and VE can be expressed in terms of the stagnation temperature. And then, of course, the mass flow rate also involves the mass inside the cartridge and the temperature inside the cartridge. So they're coupled differential equations. They're not trivial to solve. You'd have to do it numerically. Okay, so it's kind of complicated, but you could do it. So this part of the problem is hard. If you haven't done this sort of thing before, you can see that it's difficult to do. But you could do it numerically, and then once you have how the mass changes in time and the temperature changes in time, you could then calculate how the density inside the cartridge changes with time. And once you have the density and temperature changes, you could get the pressure changes in there as well. So this one is a challenge. This part of the problem is a challenge. Like I said, we didn't really cover this in ME 309, so I wouldn't expect you to do it on an exam or anything. But I want you to know you have all the tools to actually solve this problem. Really what it is just conservation of mass. The first law, this comes from ME 200. You've had this kind of material before. We're making use here of the choked flow mass flow rate expression, the ideal gas law, how you find a density from mass and volume. Here is a first law analysis. You find the temperature at the exit from our stagnation temperature ratio and the velocity at the exit just by knowing how it's related to Mach number and the speed of sound. So you have all the tools available to you to solve this kind of problem. All right, so there's a lot going on in this one, but I just put it in here just for your own reference. We'll go ahead and end the example there, and hopefully you learned something from this one.